Hello and welcome to our talk titled Faceswap, Developing a Platform for Practical Deepfakes. Who we are. My name is Bryan. This is Kyle and Matt. We are the principal devs on Faceswap, which is the leading free and open source deepfake software. So our talk today, we're going to go over a few different things. We're going to start with an intro to deepfakes, technology stack, the process of Faceswap. I actually walk you through how we do that, and then ethics and the future of deepfakes as we see it, followed by finally our Q&A. Matt, unfortunately, is a little sick today, so he's only going to join us for the Q&A here at the end. But what are deepfakes? So deepfakes are a face replacement technology. Now, what does that mean? Well, for that, I think it's best to show you.
Someone replaced Jennifer Lawrence with your face after an award ceremony, and this is her answering questions as you.
So you're a huge Bravo fan.
Oh,
Who
yes.
is your favorite and least favorite housewife of all cities?
My favorite is probably Lisa Vanderpump. My least favorite, I don't want to have to say. I mean, I don't want to have to say, because who knows when you're going to run into these people.
So, as I said, what are deepfakes? Deepfakes are a face replacement technology that works on any video or image, just like you just saw, where Steve Buscemi's face was placed onto Jennifer Lawrence. Now, it is AI-powered. We use convolutional neural networks. Sorry, that is a very hard word to say sometimes. We're using consumer-level hardware. You don't need to have any special equipment. It's not requiring high-end, specialized servers, anything like that. Using standard GPUs, available in any gaming laptop or desktop, even CPUs to a limited degree. We'll talk about that a little bit later. It does work on any videos as well. You don't need to use special equipment when recording. You don't need to have special markers or tracking. It works on absolutely any videos, and it is completely data-driven. So you don't need to be an absolute expert, an artist, skilled in any particular visual effects or anything like that. It lets you do the swap, the deepfake, without requiring a whole lot of expert skills. So how did we get here? How did we get to the stage where AI is able to replace faces completely automatically and relatively simply? Well, it begins, unsurprisingly, in academia. But over time, the technology has developed further and further from the very beginnings many years ago, where images would just be modified or altered to today, where we now have the greater ability of deepfakes. Now, the big change of deepfakes is not necessarily any great, huge step above any of those academic papers, but rather that we brought everything together into one tool, where you don't need to be an AI expert, ML expert, or even a developer to use deepfakes. Instead, it's a complete stack where you're able to go from video containing one face to a video containing an entirely new face in one package without needing extensive development. So there are several different tools out there right now. There is Faceswap, which we believe, obviously, is the best one out there. It's leading free and open source deepfake software. We've been in development continuously since 2017. We have a wide variety of developers and user support, things like that. There's also Deepfakes Labs, which is a fork of Faceswap from last year. It is currently under development as well. They have a single primary developer. Then there's the Fake app, which is inactive, although the developer says that it is still current. It hasn't seen any new updates for over a year. It is also a side fork of deepfake technology. So, Faceswap itself. Why do we think that Faceswap is the best? Well, first of all, we have full source availability. We are open source, GPL3. Anyone can download it, use it, modify it any way they see fit. We also have a very wide variety of hardware support, starting with NVIDIA GPUs, AMD GPUs. We also support Windows, Mac, Linux, BSD, pretty much anything that has a Python interpreter you can run Faceswap on, although you might not get the best speeds unless you are running with an NVIDIA or AMD graphics card. We do also support multiple GPUs, which we're the only ones among the softwares that does that, where you can use more than one GPU in a single system to train a model faster or to better quality. We have a model plugin system that allows us to have both custom models that are developed in-house as well as ported models, which we've brought in from other software. We do maintain continuous development, so we've been working on this for years, and we're going to continue. We have plans to continue doing this for at least the foreseeable future. We have a very good feature stability. We include backwards compatibility with previous models for at least, as long as we feasibly can. We do let people know, and of course you can run an older version of Faceswap if you need a particular feature that no longer works with the newer ones, or if you have an old model or whatever. But we do work to keep that backwards compatibility intact. Also, our features are very well tested. We have a large number of users, and we work very hard to do that. And that goes into the last point, which is the robust community. We have a website, faceswap.dev, where we have a forum. We have a large number of developers and users who are all very active in maintaining support and keeping things going and easy to use. And I'm going to hand it over to Kyle here, and he'll talk a little bit about our stack and how we actually do what we do.
Thanks, Bryan, for giving the overview. So I wanted to kind of go through some of the kind of technologies, some of the particular processes we go to kind of enable our software to work. So I think, wanted to go ahead and start out here is, we are based in Python. The kind of most important kind of, I think, software library of all the ones that we use is a process called Keras, which is a kind of high-level API. It's very user-friendly. It's designed to kind of allow anyone to go ahead and start learning neural networks and machine learning, building models, training models, running models through. So it's very kind of simple, straightforward, and well-documented. And that'll kind of ride on top of an interconnect, kind of in a virtual machine type of way, on some lower-level backends that interoperate with the very hardware-specific heavy optimizations to run on GPUs and CPUs in a very kind of efficient, optimized fashion. So Keras is kind of riding on top, which is the easy programmable Python level language, and it's interoperating with two backends we actually use, which are kind of extensive, fast-growing libraries, which are kind of the gorillas in the room, produced by Google, respectively, for Tensorflow, and Intel is developing PlaidML. So why do we have two backends? Tensorflow specializes in running NVIDIA GPUs as well as CPUs. We wanted to kind of have a wide user base, so we've specifically incorporated two kind of machine code learning libraries. PlaidML will go ahead and support all the AMD GPUs out there as well. So we're building kind of our models in Keras, and it's going ahead and feeding down to doing all kind of the machine learning code in these two backends. And what exactly are kind of these machine learning kind of neural networks? That in itself will probably take a couple hours of a talk, but to kind of distill it down into a couple sentences, a neural network is a computer algorithm that's designed to kind of mimic the organization of the human brain. And it's going to be learning autonomously. It's not something that you go ahead and set up with kind of specific routines or tasks. It's essentially designed to have pattern recognition or classification problems or regression. And you're going to be giving it with a task. You have a supervised learning. For example, if you're trying to do classification, you'll give it a task to classify various different images into different categories. And then you can measure the accuracy of how well this random kind of algorithm starts out with. And then over time, over hundreds of thousands, millions of kind of iterations of training, it'll kind of measure how accurate it is in doing this task and then modify itself minutely, changing kind of the math on the weights and biases of the particulars of the neural network to continuously improve, to get more accurate, to kind of minimize this loss function and to solve your problem, whether it be regression, classification, recognition. So what's a kind of practical example of this kind of very abstract, description I've given? We always talk about kind of, the Faceswap machine learning stack, and we have a couple of different neural networks. We have the kind of the core one that'll obviously doing all these swapping between identities. But even before we get that, we have a whole stack, kind of a platform hosting. We have kind of 4 separate neural networks that lead into the actual face swapping. So detection, obviously identifying a face, and then alignment, recognition, and segmentation. So I'll kind of go through each of those about how we kind of coordinate and integrate all these neural networks sequentially into each other. And then also we have a whole kind of image processing stack as well that kind of allows it to go end to end from a video to a video. So the first of those, face detection. Seems like a somewhat simple problem. Given an image, given a video, is there a face in it? Or is there not a face in it? And then kind of once you understand that problem, where exactly is the coordinates of the face in that image? Where's the bounding box that separates it? So this is sounding somewhat like a simple problem, but kind of considering all the issues of maybe it's a zoomed out shot where the faces themselves are only several pixels large. Maybe it's a very zoomed in shot where it's a headshot where it's the majority of the image. Maybe the faces are rotated or yawed or they're overexposed or they're very dark. This has kind of been a scientific problem in and of itself over the last couple of years that have advanced kind of very rapidly. And you can even see this example I'm using. It only even finds 3 out of the 4 faces. So over the last couple of years, we've actually incorporated several of the new academic state-of-the-art models. And we have 3 separate face detector networks that we can go ahead and have choices for the user to go ahead and use. So as I mentioned, the face detection will go ahead and find a face and an image, and then it will localize the coordinates and kind of draw and find out where exactly in the image it is. And then it'll pass it along to our second neural network, which is face alignment. So as I mentioned before, these faces might be extremely small, they might be rotated, they might be upside down. We need a kind of consistent, standardized, normalized format of a face to go ahead and feed off of in order to train and swap. So how do we do this? The most easiest and the best method is each face has particular landmarks. The pupils, the tip of the nose, the tip of the mouth, and the chin line, which are kind of easily identifiable. And once again, there's a neural network for a regression problem. It kind of takes in a face, and the output is it finds where kind of all the specific landmarks on a face are. It identifies this, returns us the coordinates, and then we can take those and compare them with kind of the average, mean, standard locations of face. And using kind of a point registration algorithm, we can go ahead and warp and align the face, zoom it in, zoom it out, scale it as necessary to kind of get a standardized, consistent format. So this is the face alignment problem. Once again, we've kind of incorporated several different kind of neural networks as time and accuracy has gone on. Obviously, one of the most consistent issues here is errors and robustness in correctly identifying different points to the face as people are smiling, as people are turning sideways. It's not exactly a simple, naive problem. So once we have a consistent upright pose, almost every image, almost every video, you're in a crowd, you're sitting in the front of a conference room talking to people, and you have 2 people up here, but you're only interested in getting 1 person. The face detector will go ahead and grab everyone. So most times in a video, you'll have 5, 6 different people in the shot. And we're only interested in particularly training on and swapping 1 particular person. So we have to recognize each person's identity and then go ahead and discard those people that we're not concerned about. So this is, once again, a face recognition neural network that will decompose the image of a face into a representation and encoding. So the easiest way to think about it, there's been a string of 500, 1,000 numbers that kind of are the principal components, the most important things that kind of describe and reference a face. So perhaps maybe the first number is, the color of my eyes. The second number would be, the length of my nose. The third number would be whether or not I have a beard or do not have a beard. So on and so forth. So it kind of represents the essential, quintessential features, the most important things that describe my face. And then you can compare that against, the encoding of a different face. I think I used an example here of two actors who look very similar. They are not the same person. Likewise, we are two different kind of encodings that represent how we look like. So we can identify each person in an image and then discard the identities we're not curious about. And then the fourth kind of neural network we use before we feed into the whole training process is what's called a kind of semantic segmentation neural network. So we're interested here in any particular shot that we get a crop in. There are portions of the image we're concerned about and portions that we're not. In this example, you can see the background of the blinds, the neck. These particular pixels are something we're not interested in when we're trying to learn how to describe and swap a face. So there's going to be a pixel by pixel map that kind of does a classification problem of whether this particular pixel is located in a facial area or not. And this is something that we've actually spent a good amount of time on over the last while to kind of build our own data set as well, with kind of labeled and annotated examples of faces and the corresponding segmentation maps. And also been including some of the latest kind of state-of-the-art neural networks as well as they progress and get more accurate. So necessarily too, this is important when we're looking at profile shots, when we're looking at very blurry or kind of overexposed images. You want to have an exact kind of representation of what part of the face you're most interested in. So these four kind of neural networks, detection, alignment, recognition, and segmentation, all kind of produce an output. So you take in a video with split into images, and it'll put out right now this essentially a segmentation map and the face of interest. And this will go into the core, the meat and potatoes of our training process, which is an auto-encoder, which is a fifth neural network that we will go ahead and use. And following that, we'll have some kind of more image composting and image processing as well. So what is kind of an auto-encoder? What is the core of how we learn how to do face swapping? It is a classification of a neural network that is designed to do kind of one thing, and primarily it's image reconstruction. So we'll have two separate kind of neural networks that are combined back to back. The first one is called the encoder, which is designed primarily with kind of reducing an image to a intermediate representation. It's highly compressed, something on the order of like 2% of the original data. And it's very similar to the kind of face recognition network I described before. It's going to be reducing it to the principal components, what are the most important components of this face that will allow a neural network to describe it in the least amount of information and allow it to reconstruct that face using the smallest amount of data. So this kind of intermediate representation is the latent space, as they call it. And as I mentioned before, it'll be kind of unique to each person. It'll describe kind of your particular identity using a string of numbers. 1,000 or so kind of digits typically is what the overall kind of amount of space is. So the encoder kind of compresses an image down to a latent space, and then it'll reconstruct it. And the important thing here is to realize that this is a lossy reconstruction. So we're not using pristine absolute data, but we're trying to reconstruct the original image from this compressed representation. And it seems kind of silly. Why do we go through this whole process of first compressing and then uncompressing to get the exact same thing? The important part here is we don't want memorization. We want the neural network to have an ability to reconstruct something from imperfect data. And the other very important thing is here, you can see in this example, is the input image seems to be a little noisy, seems to be a little distorted and warped. And that's another important component of autoencoders, is you have the pristine output that you're kind of trying to match as an objective, but you intentionally distort the input in order to force, one, the neural network to learn the most important features, which necessarily aren't the noise. And the neural network will automatically learn how to denoise and kind of de-warp or de-distort any input image. So in this case, this is an automatic denoiser that can go ahead and remove all the distortions that go into the input. So why is this important with faces? You can almost think of what are the differences between different people's faces. They are kind of, after all, the same thing, the same class. They are faces. but between you and yourself and your neighbor, it's merely a distortion, a warping of your facial features, how long your noses are, the colors, the particulars of the face. So we can use this framework and input essentially a face that is slightly distorted and have the neural network learn how to reconstruct the pristine original representation. So as I mentioned, encoders and decoders. How does this exactly work? I can step into a little bit more of a process. We have a single encoder that'll be working off of two people, myself and my colleague here, Bryan. They'll learn kind of the representation of how to describe our two faces into a common underlying framework, which we call the Latin space. And then we'll have two unique decoders that learn to kind of uncompress to reconstruct those images. One will be completely unique to Bryan, and one will be completely unique to myself. It'll only understand how to reconstruct my face, while the second one will only understand how to reconstruct my colleagues. So after we kind of train these networks to go ahead and reconstruct these images with a minimal error over the course of many hundreds of thousands to millions of iterations, what we can do is we can swap these decoders. We can input my face into the encoder, which will distill it down to its representation. And then instead of using the trained decoder that will reconstruct my face, we can swap it out with the opposing neural network we've used and trained on my colleague. And lo and behold, the output is my face is suddenly transformed to my colleague's. So this is the underlying concept of how an autoencoder will reconstruct an image, and in particular faces. We've kind of have 10 different networks over the course of the last 2 years that we've kind of had a mix of speed and detail, memory usage that we've tailored to different kind of hardwares and GPUs and CPUs. And also, as we've kind of increased in some of the quality and detail of this. But this is the underlying core idea and concept, an autoencoder with image reconstruction. As I mentioned, it's an autoencoder. It's a funny thing in the media. Almost any time we see something reported by reporters or kind of in the newspaper, face swaps and deepfakes in general are always described as GANs, which are generative adversarial networks. Just wanted to say flatly and succinctly, we are not a GAN. We are a convolutional neural network. A GAN has a third neural network riding on top, which is called a discriminator, which kind of intelligently decides whether or not this output is classified correctly or not, or if the quality of the output. So we have no such kind of network. The core ability of face swaps is training two kind of autoencoders, but then swapped to go ahead and aid the image reconstruction. So after we've kind of done all this training for our neural networks, the 5 sequential networks that we kind of integrate together and feed in sequentially through the platform, we have a kind of whole host of image compositing and splicing software that will take in a video, splice it out into its component frames, feed it into the neural networks, and then once we've done the kind of facial swapping, we have the output, that segmentation mask I mentioned earlier, and now a kind of reconstructed image that we can go ahead and seamlessly blend back into the background using a variety of techniques. And then we have this cropped face that we need to invert kind of the alignment process, to zoom it out, to rotate it, to yawn it up and down as we see fit to match the original frame. And then we're going to be splicing that frame back into the original video, mixing it with the audio, kind of recompressing it and making it end result video. So this kind of end-to-end process is all contained in the software, hosting all the various different neural networks, of which each of the ones I've shown you, we have probably 3 or 4 different networks incorporated in each, and then also kind of working with the image software to go ahead and have an end-to-end solution. So what's a good kind of example of this? I think we wanted to have one more example to kind of show you what the process is.
Infamous for impressions. Conan O'Brien said you do the best Nicolas Cage he's ever seen. Do Nicolas.
Oh, jeez. Well, Larry, it's an honor to be here, although I thought this was your show that you did live. I don't really know what no means, but I guess I'll go with the flow.
Now, my dear friend is Al Pacino. We spend a lot of time.
So, as you saw there, that was just another example of a deepfake putting Nicolas Cage's face onto Simon Helberg while Simon Helberg was acting and doing an impression of Nicolas Cage. So, Faceswap, again, we are an open source software. We have a robust developer and support community, run Linux, Windows, Mac, graphical or command line interface. So whichever you prefer. We are coded in Python, which is the predominant language used for machine learning and AI tasks right now. It's very, there's a lot of libraries, a lot of packages available for Python for machine learning. So that's what we're using there. So how do you actually use Faceswap? Well, the first step, of course, is to go to faceswap.dev. Our website, we have an easy installer available for Windows now, and soon we'll have an installer for Linux. It's currently in development and should be released pretty soon. We have a lot of guides for every step of the process, from extracting the data to conversion. We also have a very active and robust forum where you can go, ask questions, get answers, solve problems. Like any software, Faceswap has bugs and issues, and we recognize that support is necessary, and so we do offer that and have a very good forum there. So the actual Faceswap process, there are 4 main steps, which is to gather the data, to extract the data, to train and convert. So gathering your data, you're going to need to find videos, images of the people whose faces you want to swap. You'll get videos for both faces. Images as well can work, anything like that. Then you go through the extract, which uses the models that Kyle was talking about earlier, which will go through and find all the faces, align them, match them up, and things like that. We have a sort, which lets you actually sort by the faces to do the face recognition task, essentially. And then you would remove the incorrect faces. Training will actually use the AI to learn the faces over time. So you'll feed it in all the data that you got, and it will learn to recreate those faces. And then finally the convert, which takes in the input video, applies the trained AI on all the frames one by one, and then puts out a deepfake video with the faces swapped. So you end up with a video where all of the faces that you were originally wanting to remove have been changed to the new face. So each of those, one at a time. Gathering the data. This, along with the next step, extract, will take the most actual personal time. The most time of you actually doing the work on it. So gathering the data, you do need a variety of sources. You need to go and get videos and images from different places, different pose, lighting, and expression. Pose would be where the face is, how it's oriented, which direction it's facing, things like that. Lighting would be shadow, color, different things about how light affects what your face looks like. And then expression would be different things like smiling, opening your mouth, closing your eyes, blinking, those sort of things. Anything that we as humans can use to make expressions, of course. So then we'd actually go through the extract step, which, as I said before, takes most user time along with that previous one. So this is what will actually go through each individual frame in your source videos and extract them, getting the faces, aligning them properly in order to get you the data that you'll use to train. It's pretty simple in the basics. You put in your input video, you choose where you want to put the images, and you go. There are, of course, a lot more options, though, on there, as you can see, but I'm not going to go over them because generally this kind of talk is not the right place for that. We do have our guides, which will go over every single option, tell you what they mean, what they detail. But suffice it to say, the basics are input video, output folder, and it will go through, get all the faces, and put them all into that folder. So then we go into training. Training is going to be, I know I said the previous one steps took the most time. This one takes the most real time. The advantage, though, is that it is hands-off. You are not actually doing any work. The computer is doing all the work. All you need to do is watch over time as the model trains. This can take anywhere from a couple of days to a couple of weeks, depending on the model, your data, things like that. It is a hands-off process. But as you can see, over time, the faces that it creates are going to get clearer, more robust, and match the originals better. A good way to think about this sort of thing is it's a tripod of 3 different parts. There's the model, there's time, and there's your data. And if any of those is too short, if there's not enough in there, that's going to be the maximum that you can reach in the quality. So if you don't have enough data, if you haven't given it enough time, or if you're using an insufficient model, it's going to be the limiting force on how far your quality is going to go. And then the last step, conversion. In some ways, this is the easiest step. In some ways, it can be the hardest. Conversion is very simple in general, but there are 2 paths for it. The conversion for advanced users would be to output just the individual face. And then you can composite it back into the video using any number of compositing softwares like Nuke, After Effects, things like that. That would be a very manual process. It does take a lot of time and effort and actually skill. So while that is definitely going to be the way to go for the best quality, it's not necessarily the way that most users are going to want to go. So because of that, we also offer a second path, which is our fully automatic option, which, like Kyle had said, it will take the original face, blend it back into the frame using various features and plugins that we have for making the face fit back into the original frame. And this is really good for new users and for people who don't want to put in the effort. It's not going to get you quite as high of quality. You're going to have some problems where it's not quite perfect. But that is why we have our preview tool. So our preview tool lets you actually preview in real time the different effects from blurring, blending, different things, so that you can, on your specific data, test and see what gets you the best results live and in real time. So we have options for sharpening the image, for color correction, and even to adjust the masking and make sure that you get a good blend in between the new face and the original one. So deepfakes are a controversial subject in general, and as developers of deepfake software, we have to consider the ethical words have just escaped me. The ethical implications, that was the word I was looking for, of what we are doing. Deepfake software, like any software, can be misused, and we can't really actively prevent misuse of software, especially when it's open source. But what we can do is encourage proper use, and toward that end, we have a manifesto for our software. So we say Faceswap is not for creating inappropriate content. It's not for changing faces without consent or with the intent of hiding its use. Faceswap is not for any illicit, unethical, or questionable purpose. And Faceswap exists to experiment, discover new AI techniques, for social or political commentary, for film and media, and any number of other ethical or reasonable uses. We really take this to heart, and we actively believe that that's really the only way that any developer can go about approaching the ethical questions of a software. So what are the future of deepfakes? So we believe that one of the big futures of deepfakes is in visual effects. Movie, television, media, we really think that they will benefit from the technologies. Right now, they do face swapping. They take a face and they swap it with another. For example, they do de-aging. I saw a stand-up out here for Gemini Man, where they did an entire movie where they swapped in a young Will Smith for an older one. This process right now is done very manually. They have a large number of very skilled artists that go through and step by step, frame by frame often, paint out wrinkles or render in 3D faces in order to get high quality face replacements. But Deepfakes is able to do the same basic steps cheaper, easier, and quicker than putting an army of skilled craftsmen on it. We also think that it's able to provide a more realistic result because unlike humans, the AI is very consistent and it doesn't get tired. It doesn't do some frames less well. It does the same job over and over and over endlessly without complaint. We also believe that the future of deepfakes is going to be a good place for AI development and experimentation. Since Faceswap as a complete and total platform from A to B, video to video, you're able to swap out individual pieces if you want to try a different AI. Like Kyle was mentioning, we use different types of face detection and face alignment, but you can also use different kinds of face replacement. Or you could do, instead of faces, use hands if you find a hand aligner, or anything like that. So we think that Deepfakes is a good platform for future AI experimentation. It's also a good place for AI developers to cut their teeth. There is nothing out there right now where a developer, out there right now where developers can go and download a software package that does AI from A to Z. And they're able to go inside the code, see exactly what is happening, and modify it and see what the results are. We believe that Faceswap and Deepfakes tech gives that sort of opportunity for anyone who wants to. You can go to our GitHub, download the code, look through, see exactly how we've chose to do everything that we've done, and change it, modify it, learn, and gain experience with generative auto-encoders. As we said earlier, we're not a GAN. We are a generative auto-encoder. That is actually pretty unusual. There are a lot of auto-encoders used for classification, for identifying things, for finding things, but generative auto-encoders are actually relatively rare. We do think that there is a good place for generative auto-encoders. GANs are great, but we think in some cases they might be too imaginative, too fragile, while generative auto-encoders might help to fill that gap. So here are all of our references. Thank you for coming, and have any questions?
All right, thanks, Bryan and Carl. We'll take some questions if anyone's got any. Or not, it's fine. You can come talk to us afterwards if you'd rather. Yeah, go on. I might have to come up to you. I'm sorry?
Sorry. Okay, what kind of computing power do you need to edit a new video? Or what kind of time constraint do you need to have?
Okay, sure. You basically need a powerful GPU. Anything beyond that isn't so important. We would say at a minimum, a NVIDIA GPU with 4 gigabytes of VRAM is enough to do Faceswap. You can do it on CPU, but you're looking at months to train a model. AMD cards are supported, but generally NVIDIA cards are the best way to go. Ideally, I'd say 8 gigabyte NVIDIA card, maybe 1070 at a minimum would be what I'd aim.
My recommendation is generally to go with about an 8 gigabyte card. If you don't want to purchase a card, or if you want to just experiment, Google Colab offers free GPU access, so you can load up Faceswap. We have a notebook that lets you load it up onto Google Colab. You can try it, run a few experiments, and if you decide that this is something you're more serious about, you can get a GPU.
Yeah, one thing on on Colab is very, very useful for using and testing. Because it's free, they will shut it down after, is it 12 hours or 24 hours? So you do run into a risk of losing your model if you haven't got it backed up. But for going in and kind of playing around, it's great for that. You can do extraction and conversion locally. It will be slow locally without a GPU, but it's doable. But yeah, you'd need a decent GPU. Kind of on the AMD thing, we do try and support AMD, but AMD are way behind NVIDIA in terms of AI tech and what's supported out there in terms of neural networks. It's one of the challenges we're going to face soon, that Keras, which Carl mentioned before, is ditching multi-backend support. So us, and I'm sure others, are going to have some hard decisions about what we're going to do about AMD in future. Any more questions? I'll come to you. Just about, go on. That's certainly something that... Repeat the question. Okay, yeah, sure. So we're basically asked whether there's anything we can do to prevent the misuse of technology. From my point of view, I don't really think it's our responsibility to prevent the misuse, but there are projects out there at the moment to detect deepfakes, and they've been going for quite a while. I think, is Facebook running something at the moment to...
Yep. I mean, there's multiple kind of other techniques as well, and we're experimenting with it as well for detection of face swap as well. So kind of both on the generative of creating new videos and also detecting new videos. If people are looking at, for example, using a political figure or President Trump and swapping it in with your face, it might be a satirical issue, but it's important to kind of realize and have the ability as well to not only be able to generate these images and faces and videos for media, but also have some abilities to police it. And what better way to kind of go ahead and experiment with the techniques that generate these videos, to have another neural network that can kind of digitally sign a video that has been swapped with. But an important thing there is, yes, we kind of always go ahead and put out flat and center that these are kind of satirical or kind of film and media uses that we're going ahead and using for. And we want to go ahead and make sure that that's plainly stated that this has been created with these visual effects technologies. Just as, visual effects companies have been working on this technique for years. Notable examples, include some of the Star Wars movies and some of the Fast and Furious movies, where they had, unfortunately, an actor die before they finished the movie. They essentially use face swapping techniques to go ahead and digitally reinsert the actor into the old scenes.
One thing I'll also add to that is one of the reasons I got involved in this project is because I saw this kind of technology was out there and it was real, but it was, it's kind of hidden away in scripts and not many people could access it. And I think, if this stuff exists, people are going to develop it, and I think it's much better for it to be out and open source where everyone can get it and everyone can see it and everyone can see what it can do and know how to detect it, than it to be hidden away for whatever nefarious purposes.
And you'd also mentioned a little bit about, can we train our AI to detect illicit uses? And I mean, in some ways you can detect some illicit uses, but at that point we are in open source software. Someone could come along and remove it, or and it would take up developer time, and it could impact the quality of our other results. So we've decided that instead of focusing on that and really making that our effort, we're going to really encourage the positive uses, and hopefully we can just overcome any negative.
Sure, go ahead. Yep. You're in the red top. Okay, so that was, yeah. The question was, how long do we think it will be before deepfakes is indistinguishable from the real thing? That's a difficult question to answer, to be honest.
Which real thing?
Well,
no. Which real thing? Because, right now, I think the deepfakes is able to be indistinguishable from CG. We are able to beat CG in a lot of ways. Being indistinguishable from a real person standing there being filmed, I'm not sure. It's impossible to tell. Some people say 6 months, some people say 20 years, some people say never.
I think you could say now to some extent. I mean, there are tricks you can do to make this stuff look real. Like you lower the footage to be CCTV quality, put a load of grain on it. Could be real already.
There have been deepfakes out there used to try and influence political elections. There was one in Brazil where a man running for governor had a deepfake of him put out with multiple women to try and discredit him. What actually proved to make that video prove out to be false was not being able to detect the face swap, but being able to recognize that it was impossible for him to be in that sort of situation, that other parts of, like his arms weren't the right length or the right shape, he didn't have the same musculature, that sort of thing. And that was because the video was, as Matt had said, deliberately very low quality. They had added a bunch of grain, made it look like it was from a 1970s VHS. And it would be almost impossible to tell the details in the face, except for that the rest of the video gave it away in that it was impossible in other ways.
Yeah, I think that's true, but I think it's.
Repeat what he said.
Okay, yeah. So basically, he's saying that people don't question Photoshop photos now. So with videos, people won't question that, and I think there's a lot of truth in that. But this is going to happen, and whether I think people just need to be educated not to believe everything they see, not to believe everything they read. But I think that's been true in all of history. So, what can we do about it? Not a huge amount, I don't think.
And in a lot of ways, we are doing exactly what we can.
Put it out there so people can see it and use it and see the effects for themselves and hopefully learn that way.
The more public deepfakes knowledge is, the more people will question those videos. The more people will say, hey, wait a minute, I've heard about this thing. Maybe this isn't real. And hopefully that can lead to a more critical thinking and a more critical view on some of this content.
Yeah, about there. Okay, the question is basically which performs better out of PlaidML and NVIDIA and TensorFlow side by side. Honestly, I haven't actually done a huge amount of testing between the two because I run an NVIDIA card, so I run TensorFlow. Faceswap was originally built on TensorFlow. We added PlaidML in because we had AMD users who wanted to use it. I do have an AMD card. It is significantly slower when I switch to the PlaidML backend on both my NVIDIA card and my AMD card, but I don't have any hard and fast figures for what the difference is. And theoretically, the result which comes out should be the same.
No.
But they do things differently underneath the hood.
TensorFlow does direct CUDA optimizations, while PlaidML is OpenCL. And CUDA on NVIDIA works better, especially with CUDNN and other libraries that NVIDIA has provided for neural networks. So TensorFlow is significantly faster than PlaidML, even on the same card, NVIDIA card. AMD is a bit better than NVIDIA when it comes to OpenCL, but it's still much worse when it comes to NVIDIA's CUDA. So comparing TensorFlow with an NVIDIA card and PlaidML with an AMD card versus PlaidML with an NVIDIA card, you would end up with TensorFlow with the NVIDIA card being fastest, then PlaidML AMD, then PlaidML with a
But
NVIDIA
in
card.
terms of the end result which you get out of it, you should be looking at not in time, I mean the actual swap.
Oh yeah, yeah. The actual quality of the result will be the same with all three, but time will be significantly longer with PlaidML on both of its options. It really depends on the card and all sorts of all those other features. Unfortunately, it's not easy.
Ballpark, you're probably looking about 4 or 5 times slower on AMD, but it could be a lot less than that. It could be a lot more than that. AMD just is not there at the moment. It should also be said you can actually use TensorFlow on AMD, but you need to compile it yourself with ROCm support, and I've tried that, and it's not fun. So yeah, no, it's not easy to do. So that's why we went with PlaidML, because we're trying to make it that our software is as accessible as possible to as many people as possible. So we went with the solution which was easier, rather than trying to make someone who'd never even seen Python before have to compile their own TensorFlow wheel. And on that, I think we're out of time now. So thanks a lot. Cheers.